Hello, I'm Stella, a current final year undergraduate in Nanyang Technological University, School of Electrical and Electronic Engineering. In this video, I'll be going through the Energy Demand Prediction project. This project would not have been possible without the comprehensive guide by the AI for Impact team. So, thank you so much, AI for Impact team. Now let's begin. I always see training a machine learning model as nurturing a character so that he can perform a certain task, in this case, forecasting. As such, let me introduce to you Forky, the forecaster. In this video, I'll be going through the entire process of building a forecast model, starting from exploring the given dataset, preparing the data, identifying benchmark loss, the first naive test, feature engineering, and finally model optimization. As to nurturing Forky, we first need to understand what Forky eats. In this case, the input is the dataset by PJM, which contains hourly energy consumption in megawatts. The aim of the project is to create an energy demand forecasting model with a lead time of 5 hours. When we think about energy consumption, it is common to assume that, first, there will be a daily pattern as energy consumption varies depending on the time of the day. Second, there will also be a weekly pattern based on whether it's weekdays or weekends. Lastly, energy consumption during public holidays are also usually lower. Let's take a clearer look into the data. Here, we plotted a full week of data, and it is true that the data possess a daily pattern. There are peaks at 12 o'clock and 8 o'clock, and dips at early in the morning because most people was probably sleeping back then. We can also see similar shape daily. Next, let's take a look at the full month plot where we can see a weekly pattern. We can see dips on weekends, perhaps due to the closure of factories and offices, and maybe, just maybe, because most people were sleeping back then. We can also see similar shape weekly unless there's a public holiday. So, after understanding the nature of the food that Forky eats, let's start preparing the food and make sure that it is good for Forky. As there are some missing points in the data set that we have, we first have to do linear interpolation to ensure the completeness of the data. Next, we calculate mean, median, max, minimum, and standard deviation. Using the statistics that we have, we then normalize the dataset as a whole to ensure that the mean of the transformed data is close to 0 and the magnitude is less than 1. Forky needs bite-sized food so that it's easier for him to digest. Next, before sending Forky to fight, we need to know what is considered a credible forecast. A credible forecast must beat persistence. A persistence is where predicted future value is the current observed value. The persistence loss is simple and a useful benchmarking loss as it is easy to be calculated and it is hard to be beaten for short lead times. Here, the persistence loss is calculated to be 0.11626. This is our aim. As we have prepared the food for Forky, known a little more about what Forky is facing, and what he needs to achieve, it is now time to start training. As we start training, it is good for us to also understand the structure of a neural network, which can be illustrated here. As illustrated, we have 4 layers of perceptrons, each time shrunk by a certain factor. After that, we also have a linear combiner. We will start with a naive approach. The naive approach is where we do not use any feature but instead a naive window from t0 to t-5. We first start with a 4-layer network. Here is part of Forky's report card. As we can see, the losses graph show that the model is learning. As there are still gaps between training and testing loss, there are definitely still potential for the model to generalize better. The lowest test loss is much lower than the persistence, which means that the model is credible, but does not mean that the model is perfect. Here, we can also see that the model is better with bigger NN size. This is not a definite conclusion, but it's a good gauge for us. In the second part of Forky's report card, we can see that the actual and predicted results are pretty close to each other for both trained and test datasets. This means that the model is able to generalize and not merely memorizing. In the scatter plots, while it's not too bad, we can still see some dispersions. The lag correlation graph shows us peak at 1. This surely can be improved. To further improve the model, we will now guide Forky to view the dataset more smartly by using feature engineering. Based on the patterns identified earlier, we add 4 features based on the daily pattern, where we consider the minimum, maximum, mean, and difference. And based on the weekly pattern, we add 3 more features, minimum, max, and mean. To help us identify the ideal NN sizes, we also sweep higher NN sizes of 64, 128, 256, and 512. Forky sure learns better now. As we can see, both training and test losses are lowered significantly. The gaps between training and test losses have also narrowed, which means that the model can generalize even better now. It is worth to note that the conflicts with higher NN of 512 does not bring lower loss, but instead 256 brings the best loss. Forky sure learns better now. As we can see, both training and test losses are lowered significantly. The gaps between training and test losses have also narrowed, which means that the model can generalize even better now. It is worth to note that the conflicts with higher NN of 512 does not bring lower loss, but instead 256 brings the best loss. Let us now see the prediction plots. Here we can see that the scatter plots are much more linear compared to the naive approach. The peak of the lagged correlations has also moved to 0. This is a great sign that the model is learning very well. As to anything in life, we should always seek further improvements. After performing feature engineering, let us now optimize the model. First, we will attach a dropout layer to the perceptron so that each perceptron will randomly drop data points with the rate that we assign. Here, we set 0.05, 0.1, and 0.25. Since we see better learning with NN sizes of 64, 128, and 256, we will always sweep those. In this step, we also apply a rectified linear unit or value saturator. Let us repeat each config for 5 times so that we can also identify combination with the lowest deviations. Let us see how the model performed. Here, we can see that the test loss continued to lower, beating persistence loss and even the previous loss, which was 0.00758. We should also note that the best performing dropout rate here is 0.05 and the best NN size is 256. However, when we compare the sizes of 128 and 256, the improvements are insignificant, and as such, it might be good to use the NN size of 128 so that we can continue to obtain low losses while making sure that the resources needed to perform the forecasting is low. The scatter plot has become significantly more clustered around the line, and the peak of the lagged correlations remain at 0. This is a very good sign. While the previous results are decent, we will want the best for 4K. Let us now improve the model by keeping the dropouts to be 0.05 and then sizes to be either 128 or 256, applying the value saturator. Here, we also add a Weyl decay of 10 to the power of negative 5 and apply a L2 regularization. To see how much the results deviate from each other, we repeat each of the config 20 times. Due to a very busy server and time constraints, I'm unable to obtain the graphs. A lower loss and an even more linear scatter plot is expected here. We will then use the best configs in the final model. The model also can be improved further with these ways. Now 4K is ready to be a forecaster. Thank you so much for following our learning journey.